Today, we're diving into some really mind-blowing research on a new type of material that can quite literally feel when it's breaking. We're talking about smart composites that could build a future where our bridges, our planes, and even our ships actually warn us before a disaster happens. I mean, just stop and think about that for a second. An airplane wing that sends out a signal saying it has stress fractures. A ship's hull that alerts the crew to damage right after a collision. This isn't science fiction anymore. This is the whole idea behind materials with a built-in nervous system, and it's the huge challenge this research is taking on. So how in the world do you do that? Well, the goal is to make materials that are not just strong but also smart. And the secret sauce is something called piezo resistance. Basically, you embed a damage-sensing ability right into the fabric of the material. Think of it this way. When the material gets stressed or cracked, its electrical resistance changes. It's almost like it's crying out in pain, but with an electrical signal. Okay, so to find the best possible design, the researchers basically set up a competition. They created and tested two main families of these smart materials. First, you have the intralaminar composites. These are pretty straightforward, just simple stacks of different carbon and glass fabric layers, one on top of the other. Then you have the intralaminar composites, where things get way more intricate. Here, conductive carbon and non-conductive glass yarns are actually woven together into a single complex fabric. And here's the lineup for our big stress test. You can see the simple layered types, the inter ones, and then the more complex woven intra types. Now, those numbers you see, the 0, 90, and 45, that's just the angle of the woven yarns. And as you're about to see, every single one of these designs creates a totally unique internal structure. That structure is going to decide both how strong it is and how well it works as a sensor. And here you can really see the difference in philosophy. On the left, that 0/90-degree weave makes a simple, rigid electrical grid with its carbon yarns. But look at the right. The 45-degree weave creates this much more complex, intersecting diamond pattern. So the big question is, what makes a better sensor? A simple grid or this complex web? That little structural difference, well, it turns out to be everything. All right, so you've designed these amazing materials that are meant to handle things like high-speed impacts. How do you actually test them? You can't just pull on them slowly in a lab. You have to simulate the kind of sudden, violent, dynamic force they'd face in the real world. And that, right there, is a pretty serious engineering challenge. This is the beast they built to do it. It's called a split Hopkinson pressure bar. The simple way to think about it is like a high-tech slingshot. A gas gun fires a projectile, which sends a crazy powerful shock wave down that bar, literally ripping the material sample apart at incredible speeds. And the whole time, a battery of sensors and high-speed cameras are recording exactly how it breaks and, crucially, how its electrical signal responds to the damage. So after all that violent testing, the results started coming in, and this is where the story gets really, really cool. It wasn't a simple case of one material being the best at everything. Nope, it was a split decision. We ended up with two very clear winners in two completely different categories: pure brute force toughness and finely tuned damage sensing. Let's talk toughness first. This is all about how much energy a material can soak up before it finally cracks. And we have a runaway winner. The GNR composite, one of those simple layered designs, was by far the toughest. It absorbs 741 joules per square meter. I mean, that is just a huge amount of punishment it can take. But who was the best sensor? This is where my jaw drops. The results completely flipped on their head. The winner, by an absolute landslide, was the G45/C45A composite, the one with that complex 45-degree woven pattern. Just look at that number, an absolutely insane 1,168% change in resistance. This material doesn't just send a signal when it's damaged, it screams. So this is the big reveal, the core takeaway from the whole experiment. The toughest material was actually one of the worst sensors, and the best sensor was one of the least tough. The simple layered structure is like a brute. It's amazing at stopping cracks. But the complex woven structure is like a detective. It's way, way better at detecting them. And that creates a really fascinating trade-off for engineers. This, of course, raises the big question. Why? Why on earth was the simple stack of layers so much tougher than the intricate weave? To figure that out, the researchers took the broken pieces and put them under a scanning electron microscope. We're going to go on a microscopic tour, and what they found reveals the secret to each material's unique personality. Okay, so first we're looking at the fracture surface of one of the tougher woven composites. If you look closely, you can see the clean, snapped ends of the individual carbon fibers. To break this material, you have to physically break thousands upon thousands of these super strong fibers, and that just takes a massive amount of energy to do. Now, let's compare that to the champion of toughness, the GNR composite. See the difference? It's huge. Instead of all those clean fiber snaps, you see massive cracking and separation between the layers of fabric. This is a process called debonding, and it basically acts like a giant internal shock absorber. It dissipates a huge amount of energy, and that's the secret to its incredible strength. And finally, let's look at our master sensor. It wasn't the toughest because its angled fibers just couldn't carry the load as well. But here's the kicker. Its weakness was also its greatest strength. That complex 45-degree weave created an incredibly dense and sensitive electrical grid. Any tiny little crack was basically guaranteed to cut through multiple conductive pathways at once, causing that huge, unmistakable spike in resistance. So now we have a champion of toughness and a champion of sensing. What this research really does is give engineers a design playbook. For the first time, it shows them exactly how to choose between pure resilience and built-in intelligence, or how to blend them, all depending on what the job is. So let's just quickly recap the big takeaways. 1. If you need pure, simple toughness, layered designs are your best bet. 2. If you need to sense damage, woven designs are way, way better. 3. That 45-degree weave is the undisputed king of sensitivity. 4. And this is a big deal for manufacturing, these woven designs are smart right out of the box. They don't need any expensive nano additives. The carbon yarn does all the work. And finally, kind of a cool bonus, all of these materials actually get tougher when you hit them fast, which is exactly what you want in a high-impact situation. So what's the bottom line? Why does this all matter? Well, this research provides a clear roadmap for creating structures that can monitor their own health in real time. We are talking about naval ships, commercial airliners, bridges, and buildings that can tell us exactly when and where they are damaged, long before a catastrophic failure can even happen. It's a brilliant way to build a safer, more reliable world. And that leaves us with one last thought to chew on. For all of human history, the materials we've used to build our world have been silent. They've been mute. And now, they're starting to find a voice. So the question is no longer just what can we build, but what becomes possible when our creations can finally tell us they're hurting.